Alright, hey guys, what's going on? So today we're going to be covering something that we typically don't really cover in any sort of general relativity course. This complexions, and complexions are going to help us understand more electromagnetism within the context of GR. Again, this is somewhat of a weird lecture or a weird discussion today because, again, these are things you don't really hear about. But we're going to get into them. We're going to see how they're important mathematical objects, and from there we're going to continue with electromagnetism in GR. And then after that, we're going to move on to conformal theories in GR. So let's get straight into it. So again, make sure to hit that like and subscribe button. Make sure to go onto my Patreon page if you want to see notes on these videos as well. So we're talking about complexions in curved electromagnetism. And we're going to start off by considering just an arbitrary vector or bivector f be a complex electromagnetic vector defined in this way. So E is the electric component, B is the magnetic component. Together they construct this bivector, which is f, again because the electric vector is a vector, and then the magnetism can also be construed as a vector, which is why they're bold. Right, so this is why this is called a bivector. It contains two vectors inside of it, and we're calling that f. So now we're going to consider the electromagnetic vector, and we could see that f is a result of a complex rotation of big F. Big F is going to be big E, which is, again, electromagnetic vector, the electric part of the electromagnetic vector, and B likewise is the magnetic part. Okay, we've gone over this a little bit already. We've seen how we were validated in construing a theory in which the magnetic part is the complex part of a general bivector, and the electric part is the real part. Okay, and so in this way, again, we can rotate this vector f in the imaginary plane because it's an imaginary number, and we get something that looks like this. Okay. The point here is that when we do this rotation, we need to rotate it by some angle, okay, and that angle is going to be called alpha. And so if we look here, alpha, this is our complexion, okay. This is what's going to be important in understanding electromagnetism within the context of GR, okay. It's this angle by which we're rotating bivectors, okay. And so let's go more into this. So this means that we can rewrite this as a rotation matrix, where f is that we have this rotation matrix inside the imaginary plane, and we're rotating the original electric and magnetic vectors. Okay, and so therefore we get something that looks like this. And the variable A, again, as I mentioned, is called the complexion. It's important in the topic of electromagnetism because Maxwell's equations are invariant under this type of duality rotation. So under a rotation in which this complexion is involved, then we can understand Maxwell's equations as being invariant under this rotation. Okay, in other words, the electromagnetic field does not change under this type of rotation by some angle alpha. Okay, so we can calculate this. So we can actually calculate this complexion, and so we begin our investigation in this complexion by invoking covariant derivatives here. Okay, so here again, our bivector f mu nu written in component form. We can take the covariant derivative here with respect to gamma, and when we do that, we can construe f mu nu as the rotated form of big F mu nu, as we've talked about up here. Okay, big F is this one, right? So this is just a rotated form, right? We have cosine alpha, sine alpha. Here's a cosine alpha and sine alpha. Likewise, we can do the same for our dual, the dual of our bivector. We've talked about the dual of the bivector as well. That was associated with flipping signs within the matrix, right? So You can go back into the videos talking about self-duals and the duals of bivectors and all that. The point here is that we can take covariant derivatives of these bivectors, right? Because, again, if we go back all the way back to GR, we should be able to do this, right? Because these things theoretically are tensors located at every point in space, time, and at every point in space, time, we have this covariant derivative as well, so we should be able to do this, okay? Or to do these operations. And so when we do that, we get this, right? So we're just taking derivatives now, and we see when we take these derivatives, we get these guys here, okay? And then we need to take the derivative of alpha as well, so that's the product rule, okay? And then we have so we have these guys here, and then it follows that we get these here, right? So again, because this here is just this one, okay, and this here is just this one, all right. So it follows. So this, when I was typing this out, this guy just sits on top of the bivector. But anyways, these relationships hold where we have so this here, we're just going to take, so we take this guy right here, okay? That's this right here. We multiply both sides by f rho mu, and we get these relationships. And so these are going to be useful to note later on, okay? So summarizing the two equations, we can get, or summing, not summarizing, like summing these two guys, we get this, and so we sum these two guys to get this, and then from here we get this, okay? And this was a relationship that we've established before also, and we can see this, right? So here we have rho, again, I like color coding, rho and rho, and then nu and nu and nu, just to see where everything is going here, and then mu, and I'll do yellow for mu. Right, so you can see here that these are the dummy indices, okay, and then I'll do dark blue for nu, and then we also have dummy indices here as well as dummy indices right here and here. So you can see how this works, because now we'll be able to use this equation right here, and you can see also how we got, so again, this was a relationship that we established before, to get from here to here, okay? This was that relationship we had talked about a couple of videos ago when we were talking about bivectors and self-dual bivectors. So the complexion, so if we remember that our complexion, let's see here. So the complexion is going to be, so here's our alpha, right? So we need to calculate alpha. So to do that, we're dividing both sides by all of this here. Okay, that's all of this. We're multiplying both sides by 2 because of this guy. And then we have all of this here is all of this, all right? And then we're putting a rho here, which is this right here, right? So we're defining the derivative, or the gradient. We're defining the gradient of our complexion a little bit differently here, where we just assign this is shorthand. Right? So this can really just be thought of as shorthand. Right? So now that we have this relationship locked and loaded, we can now go back to our this bivector here that we established before. So again, this came from decomposition of the Riemann equation, right? So for the Riemann rho nu, this thing was a natural a three-part decomposition from our Riemann curvature tensor, and we found it to be this right here in our last video. We could take the covariant derivative of this tensor, and we get this right here, okay? And you can sort of see how this works, right? Because we have covariant derivative, all throughout these terms, and so this thing is being applied to all four, or to both of these terms. It's giving us four terms because we have product rule. Okay. Recall the right dual of this tensor is this guy, which is we defined it as this guy. Again, I just want to emphasize that f, little f here, that's just an arbitrary bivector, right? Where this is the bivector that are electromagnetic. It's our electromagnetic bivector, okay? And it's rotated, okay? Okay, so we can contract the tensor with its right dual, right? So this is where things get a little bit math heavy, and so I color-coded a few things to hopefully guide us through this process, as you can see. So we're going to multiply our covariant derivative with our right dual, okay? And when we do that, you could pause the video, we get all of this, right? So we're literally just multiplying this here with this here. And so we get a lot of FOIL that happens, right? So this times this guy, which is going to be here, and then this times this guy, which is here. And you can see we have 1, 2, 3, 4. So we should have 8 terms here. 1, 2, 3, 4, and then 4 more. So we have all of this. This is a big mess. Okay, again, you can pause the video if you want to continue, go through this in more detail. Or if you want to slow down also while going over this. So we can realize also this fact here. So this was a little bit, this is nu on top, sigma on bottom, okay? But we can realize that, again, I'll color code a few things, rho, nu, sigma. So our nu's are, so here's our sigma. Right, so then we are summing over the nu's, and summing, and the mu's are also dummy variables. So mu's are dummy variables also. Right, so that's how we can make sense of this guy, this relationship. So this equals 0, right? Because so we're summing over these two guys. And when we sum over, let's see here, this equals 0 because we have, these are complete, right, because this is mu nu, this is mu nu. So this, that's going to go to 0. And we have established that before also. And so we get, no, not because of that, right? Because of this. This is going to be 0 because these two guys are different. Rho and sigma are different. Right? So then we can realize that this is 0. Okay? So that's useful because now a lot of things will cancel. And the things that cancel in this term up here are the things that canceled out in red. And we're left with everything color-coded here. So this term here is this term here, this one, this one, this one, this one, and this one, this one. And then if we recall that this here, again, this isn't too difficult to see because we just have, these are duals. These ones are not duals. And if you recall from a few videos ago, that these were just different by a sign. So we can get, so with this, we get this here. Okay, so again, I'm tracking all the colors. So this term here is right here. This one is right here. And we're factoring out rho sigma, rho sigma. All right, so rho sigma, rho sigma, rho sigma, rho sigma. We get that negative. Okay. So when we factor out the negative rho sigma, then this guy here has to be positive, right? Because of this relationship. So that's why we have this positive sign here. And this one is positive also. Okay. Okay. So now so and then these two terms here, these two are just this term and this term. So we can note also this here is equal to this, right? Because this is the dual. This is how we define the dual through this relationship. Okay. And so just zooming in on here a little bit, we can get this is our term. We just bring it out. And then we have all this multiplied by this in here. Okay. And then when we do that, we have, let's see here. Looks like I actually didn't do much kappa lambda nu, kappa lambda nu. And then I switched. This was anti-symmetric, or this has this symmetry, right? The Levi-Civita. Rho sigma over here, right? So here's rho sigma, and there's rho sigma. Okay, but then we can realize that when we do this here, this all stays the same. So this all stays the same, and we just get the kappa, the kappa lambda. Okay. Again, because this is the definition. This was a definition when we were talking about right and left duals. It's just that this is not a rank 0,4 tensor. This is a rank 0,2 tensor. So this actually makes things a lot easier. These two rho sigmas are going to sum over each other, and we just get that same symmetry back, but in kappa and lambda. Okay, so we could see now that this lower index on the left side of the derivative, and then upper index on the left side of the derivative over here. It's just that so we're sort of in a sense raising indices and shifting the duality on different sides of the derivative. And this is a useful little trick to know, right? Because we have now we know how to flip duals across derivatives, right? And we know how to raise indices as well. So that's a useful little mathematical trick to know, okay, when we're talking about bivectors. And also, okay, so we've established this relationship here, and that relationship is right here. So that's this first little tidbit that we have. And then, okay, so let's talk about this one using this relationship that we have established up here. Okay. We could take the derivative. Okay, so when we take the derivative of this guy, we get this. This is just the chain, or what's it, the product rule, right? The product rule. And this is going to be 0 because this we said was 0. So that means that this here is just this here. All right, so what's this? Again, we're flipping, or we're swapping duality across the derivative. And we are, here we're raising indices, and here we're lowering indices. So that is this right here. Okay, so we have this rule here. So this rule here is raising indices, and flipping duality. Okay? And here, so we were able to show that when we do that, we get this, but we also get this here. Okay? And so this is okay, so we have that, and now we also have this relationship here. Okay, so this relationship here is rho sigma, rho sigma, rho sigma, rho sigma. The only difference again is duals on one side, non-duals on the other. Okay? Alright, so now that we have all of that, we can put things into this equation here. So we have this, right? So okay, let's go up for a second. That's this right here. Finally get an equation for the contraction. So what ends up happening is that a lot of these are going to go to 0. Right, so we have this term here and this term here. So I should have color coded these, but this is the green term. This is the yellow term. Okay, these two terms are going to go away because of these relationships that we've established here. So we have this here, the negative, right? So let's see here. So we're raising the index, or we're raising these two indices, the duality is traveling across the derivative, so we get this negative sign. Okay, and so we have, so let's see here, and then we have this one and the same thing. Looks like something might have happened in the calculations. So we have, let's see, because here it looks like I'm saying two different things, or two things that are contradictory to one another. So I think, let's see, if I come back up here really quick, I just want to double check. Let's see. So we note, so this relationship is this first one. And then this one moving. Let's see, this here. Oh. This is the definition of the dual. So we have the dual over here. Okay. So this is the one that I think we might have messed up a little bit, because these should be opposite of each other, right? These should be opposite of each other, so they cancel out, right? So these guys cancel out. Let's see here. Those guys will cancel because of these relationships. But this relationship here, we actually, let's see here. So, oh, I think I found out. So this here was 0. This is 0. And we have an upper index here with the lower index. So, okay, those aren't indices. This is the problem. So we can actually forget about this relationship for right now. Okay. Because this is the dual on the upper index. This is dual on lower index. So this might not actually be 0. So we'll forget about this for right now. All we really need is this term, because it tells us that this is going to go to 0. Okay, and we're left off with just this part here. Okay. Dividing both sides of the equation now. So let's just go back really quick. So here's our equation. Okay. So now, so we have this. It was equal to this right here. Okay. If we divide both sides by, we could see, okay, so let's actually do this. So divide both sides by this. Okay. So that is where we get one of these terms. All right. And then, so we have this. If we divide again both sides by this term, that's where we get the second, that's where we get this guy. But then we need a squared on this guy. And then we just have dividing of this and multiplying of this. Right. So multiplying of that, dividing of that. Okay. So we have now this here. Recall that the equation we found for the complexion was this guy. So we can now start plugging things in. So alpha of t, or tau, this is again the gradient of our complexion. We get this. Okay? Now we call the equation we developed from the contraction of the Ricci tensor. This was that equation that we got from contraction of the Ricci tensor. And so this was, so we can get from here to here just through a bunch these few calculations. So we get f and f dual. This is how we define them. Again, this is just rotation of some arbitrary bivector. And then we get these two guys. Right, these, so we can, these come from trig relationships. Okay. And so we can say, excuse me, we could say this squared plus this squared is equal to this squared. Right. So, again, from these we get this equation. Okay. Because when we square this, we have to square this side, and we have to square this, we square this side, and then we could subtract both equations, and we get this. So that means that this here is the square root of the sum of these two guys. And so if that's the case, then we could see how we get from here to here. Okay? All right. So now the covariant derivative of our tensor, this going back to our earlier video on the decomposition process, we just take the derivatives now of every term to match the Einstein field equations, again with our divergence of our tensor, our Einstein tensor has to be 0, so the divergence of our Riemann, or our Ricci tensor has to be 0 as well, so these two guys go to 0, and we get these guys left over, right? Because we're raising nu, and this should be raising mu, right? This should actually be mu. Actually, wait, let's just double check. That's right. no. So we have let's see. Oh wait, no. So I see what's going on. So two of these terms are going to add with each other. So and let's see, r rho nu. So here's r rho nu, and here's rho mu, right? Okay, that's rho mu, and let's do sigma nu. Just going to color code these guys just to make sure everything's kosher. So sigma mu down here, that is going to be, where'd that color go? So this color here, this guy. And then sigma, or rho nu is green. All right. So these two guys, let's see what happened to those two. So those two guys, we have, oh, this is why, because this has to go to 0 and this has to go to 0 because of this, right? So this should actually be nu, right? So this term and this term, because we found this earlier in our Einstein, with the divergence of our Einstein tensor, that these two guys therefore have to go to 0 because of this relationship. So we're demanding that this have a 0 divergence. So the right dual of the tensor is going to be, we've defined it in this way, and when we do that, we have all this, we're raising all these indices, and again, you could pause the video, I'm not going to go too deep into all this. We have this, and then we get all the way down to this point here. All right. And so we find that the multiplication of our divergence with our right dual is going to be this here. Okay. And where do we get all this? So this here was this. This here is this relationship with, so this here is our E right dual. When we multiply everything together, multiplying everything together, so the 2's multiply to the 4's, and we can factor out these mixed index Riemann or Ricci tensors, right? So that's going to be this guy, and there's going to be some dummy indices that we sum over. So some of the indices are going to change their name. Again, you could pause the video to see how this works, because again, I'm already over 30 minutes here, and I don't want this to go on for too long. But so we get to this point where the divergence of this tensor multiplied by the right dual is going to be the divergence of the Ricci times the mixed, this mixed term. Okay. Okay. So what does this all tell us? So we've gotten to a point where we define this, and the complexion didn't really show up here, but now what we can do is we can say, if we take a look at this, okay, and we take a look at our complexion, we have this, right? Because our complexion, it said, well, this was a right dual multiplied by the divergence. So we can recall the definition of our complexion. We can substitute this in with this. Okay, the 2's cancel. And this is our complexion. This is how we actually write the complexion in terms of the Riemann or the Ricci tensor. So recall that the Ricci tensor exists at every point in space-time, and that this tells us something about how volumes change along geodesics and curved space-time. Okay, that was something we talked about a while ago. The complexion is an angle of duality rotation in which the components of the duality rotation are vectors themselves, right? So the electric and magnetic vectors. The complexion is also a scalar field because it's just an angle that is non-arbitrary for any smooth Riemannian manifold. So what this is telling us is that at every point in spacetime we have some scalar, and that scalar is the complexion, and that complexion tells us how much we've rotated from the real axis, okay? And so we can imagine here we have a scalar field, green being, say, high levels of angle rotation, and red being low angles, okay? And because this complexion field is a scalar field, its curl is also going to go to 0. So this is called the Reinich-Meissner-Wheeler differential condition, which looks like this, okay? This is just to say that the curl of the scalar field is 0. The curl vanishes then by the fundamental theorem of calculus, and we see that, we know that A of this complexion is a function of spacetime, and if there's singularities on the manifold, then the line integral around any closed path is also going to be a multiple of 2 pi. This is so a closed path along this complexion field is going to be some n multiple of 2 pi. Okay, this is something that we're not going to cover in quite depth, partly because this video has already gone over 30 minutes, but also partly because I want to keep these videos somewhat contained, okay? Or not contained, but I want to keep these videos somewhat as short as possible as I can. And so, with that being said, this was somewhat of a complex video, but we've gone over something interesting, these things called complexions, and these complexions help us define the relationship between two bivectors. And when we're talking about bivectors in this context, we're talking about electromagnetic bivectors, or the electromagnetic field tensor. So we can imagine rotating these bivectors, if you will, or these tensors, and that rotation tells us that rotation is encoded in this thing called the complexion. Okay. So with that being said, I hope you like this kind of content. Make sure to hit that like and subscribe button. Make sure to go on to my Patreon page if you are interested in that, or if you're interested in getting notes and supporting the channel. So with that being said, I'll see you guys in the next video. Bye.